Hi everyone, my name is Maren Tahan. I'm a principal software engineer at the Office of the CTO in Red Hat, and today I'm going to talk to you about eBPF. I'm going to focus on the cloud native networking application point of view. So I'm going to start by introducing what eBPF is. We're going to discuss some of the challenges that eBPF users and developers face when trying to deploy an eBPF application. We're then going to discuss how we can use eBPF for cloud native networking applications. I'm going to demo one such application, and then we're going to summarize what does this all mean for Edge. So what is eBPF? eBPF is a kernel technology that evolved from classic BPF. It's been around since the 4.4 kernel and can be thought of as a framework that allows you to extend kernel functionality by running programs at various hook points in the kernel. Some people like to think of it as lightweight sandboxed VMs. What happens with eBPF is an eBPF event flares, your eBPF program runs to completion, and this program can actually interact with kernel resources using special functions called eBPF helpers. Because eBPF is natively integrated in the kernel, you don't need to do any kernel development, you don't need to write any modules. And this is a migration from the traditional development and upstreaming lifecycle that kernel-dependent applications have had to date. There are a lot of applications and projects that use eBPF. I show a snapshot of a few here on the right-hand side. There are many, many more. Generally, these applications fall into one of three categories: networking, security, or observability and tracing. And from a cloud native networking point of view, most of the focus to date has been on infrastructure networking. So where is eBPF used? Well, we know that eBPF has been used in production at Facebook, Netflix, and Cloudflare for quite some time. And I suppose anywhere where Cilium is being used in production today as well. So what are the challenges that eBPF users and developers face when trying to deploy an eBPF application? So starting with the development point of view, there's a component in the eBPF framework called the verifier. And the job of the verifier is to make sure that your program is safe to run in the kernel. If you have a networking eBPF program that parses or touches a lot of packet headers, it can be difficult to get your program through the verifier. Some people even consider it a bit of an art form. Secondly, you need to treat eBPF programs like you do root privileges. These programs have the capability to see literally everything that's running on your system. So you need to be careful about what programs you allow to be loaded on your node, and you need to ensure that you have completed some comprehensive testing on these eBPF programs, so that not just any application can come along and load an eBPF program at will in your system. Which brings me to my next point. So right now, there's a lot of tools out there that allow you to load and unload eBPF programs. Lots of projects leverage these tools or have their own ways of managing their eBPF programs. But if you take a step back and look at things from the point of view of being able to prioritize or apply policy to eBPF programs on a node, there's currently a gap or nothing that really addresses that. So, you want to make sure that no eBPF programs are stepping on anybody else's toes or being able to manage multiple eBPF programs with some level of priority at different hook points. These are all things that you probably will want to do with eBPF programs. Actually, Red Hat is working on a project currently called BPFD, which hopes to address some of these gaps. Lastly, from the point of view of portability, if you wanted to deploy an eBPF program on a target machine, in the past, you've actually had to make sure that you compiled that program on the target machine. So you needed to make sure that the tool chain and the kernel headers were all in place to allow you to do that. Luckily, due to the advancements with core compile once run everywhere, as well as BTF, the BPF type format, you no longer need to do that. You can compile your program once and run it on multiple targets. And then that brings up the question of, well, how do I distribute my BPF program? And actually, Project Bumblebee has a very interesting approach whereby they use OCI compliant images to allow you to distribute BPF programs. BPFD will also allow you to do that. So taking all of these things into account, how can eBPF be used for cloud-native networking applications? Well, one possibility is to leverage an open source project called Cloud Native Data Plane, or CNDP. And CNDP is essentially a cloud native packet processing framework that gives you three things. Firstly, a collection of user space libraries for accelerating packet processing for cloud applications. These user space libraries are based on the performance principles of VPP and DPDK. However, they're completely abstracted from the underlying infrastructure and don't have any of the strict resource demands. The second thing that CNDP gives you is a hybrid networking stack that interworks with the Linux networking stack. So you may have heard of user space networking stacks, and these networking stacks typically either re-implement kernel functionality in user space, or if they do interact with the kernel, have some pretty complex models to re-inject traffic back into the kernel to be able to interact with the kernel. So essentially, when traffic arrives on a network interface for these type of stacks, all traffic is redirected to user space, and then that stack may re-inject packets to the Linux networking stack. With a hybrid networking stack, when traffic arrives on a network interface, non-application specific traffic is passed directly through to the Linux kernel, and application traffic is passed up to user space where a very lightweight, high-performance networking stack is running. Your application can interact with this networking stack either via a socket-like API, or it can be tightly integrated with the application stack with this networking stack itself. And this networking stack is essentially leveraging the kernel to learn the routing and forwarding information for the app. So the kernel is doing the heavy lift. The user space networking stack is simply pulling that information from the kernel and then processing packets and sending them to wherever they need to go. The third thing that CNDP gives you are the Kubernetes components to provision and manage a CNDP deployment, and specifically AFXDP deployment. So CNDP provides you with an AFXDP device plugin and an AFXDP CNI. So allow me to introduce AFXDP before we talk about those components in a little bit more detail. AFXDP is a new socket in Linux that allows you to redirect traffic from the driver directly to user space without having to traverse the full Linux networking stack. It essentially takes advantage of an eBPF program attached at a hook point in the driver itself called XDP, or Express Data Path. And when AFXDP is leveraging this hook point in the driver, it's said to be operating in native mode. However, not all drivers support AFXDP or support this XDP hook point natively. And in this scenario, AFXDP falls back to another BPF hook point a little bit further up in the networking stack, the TC hook point specifically. And when AFXDP is interacting with this TC hook point, it is said to be operating in generic mode. And what this means is that any networking interface today can leverage AFXDP, even if that networking interface doesn't natively support the XDP hook point in its driver. And AFXDP actually shows them very, very promising performance. So CNDP provides you with an AFXDP device plugin and an AFXDP CNI. The AFXDP device plugin manages the loading and unloading of eBPF programs on the networking interfaces on the node, and then the CNI will plumb those interfaces to your pod. And just to highlight that with the device plugin and the CNI, the privileged operation of the eBPF program portion, or management of the program portion, is abstracted out from the application or from the pod. And so your pod can run now completely unprivileged, because the device plugin is already a privileged application running on the node. It completely makes sense to abstract out all the privileged operations into that entity itself. So how does CNDP address the eBPF challenges that we spoke about a little bit earlier on? Well, firstly, you don't have to write any eBPF programs. The kernel provides standard AFXDP redirection program that you can take advantage of. As I mentioned, with root privileges and so on earlier on being a challenge, with the device plugin and CNDP, you can support running completely unprivileged pods. This is very different than any existing eBPF applications that you want to use right now. From a eBPF program management or orchestration point of view, CNDP doesn't really address this. The device plugin actually manages the loading and the unloading of the eBPF programs for the CNDP pods. But realistically, in the future, closer integration with projects like BPFD is going to be essential. And lastly, not so much portability, but more distribution of your eBPF program. This is, again, not an issue because the FXDP program is inbuilt to the kernel itself. So I'm now going to demonstrate a hybrid networking stack application that uses both CNDP and FRR. FRR is a standard IP protocol, IP routing protocol suite that's available for Linux and Unix. So we're going to use CNDP's hybrid networking stack to showcase how we can filter traffic to the appropriate endpoints. And in this demo, what we're going to do is we're going to run 4 Docker containers. We're going to have client 1 and client 2 residing in 2 different networks. We're going to launch 2 vrouter instances, CNDP FRR1 and CNDP FRR2. On these vrouter instances, we're going to run the CNDP hybrid network stack on 1 instance, and on the second instance, we're just going to run vanilla FRR. We're going to use OSPF to do path learning, and essentially, we're going to eventually be able to connect client 1 to client 2, even though they reside in 2 completely different networks. Okay, so let's start up by actually checking if there's no containers running right now, and let's start up the demo script that'll generate the different networks. It'll also create the different Docker containers, and it will plumb the different containers to the different networks. And actually, while that's doing that, let's discuss. Let's just zoom into the CNDP FRR node in a bit more detail. So the CNDP FRR1 instance is actually going to run the CNDP FRR hybrid networking stack. It's going to have 2 vEth interfaces, one connected to network 1 and one connected to network 2. And we are going to inject our AFXDP or eBPF program on each of these vEths. And this eBPF program is going to filter non-application specific traffic, non-UDP traffic, directly to the network, and it's going to filter UDP traffic directly to the AFXDP sockets attached to the CNDP lightweight networking stack. Both FRR and CNDP network stack interact with the kernel network stack via netlink. So we're going to be able to see CNDP's routing and forwarding information being pulled up from the network stack. Okay, so let's have a look now and see that we have our 4 containers, which we do. CNDP FRR1, CNDP FRR2, client 2 and client 1, and let's just try and ping from client 2 to client 1. So 172.19.0.2 was the IP address of client 1. And of course, we can't ping from client 2 to client 1. We haven't started neither CNEP or FRR on any of the view routers at this point. Okay, so let's go ahead and start them up. Let's start by starting the CNEP application or the network stack. So we can see that SKB mode is enabled or generic mode is enabled right now. We can ignore these UMAM reports of failure. These are just an issue with some of the channel retrieving information on the VETH. I'll have patches submitted for that very, very soon. And right now, TCP is disabled on our networking graph. I only have UDP configured. So if we go ahead and have a look at the routing information on the kernel side, we can see that it can see two networks, 172.19 or 27, that's 172.19.0.0, 172.20.0.0, and it should be the same on the CNDP side. So just to show you as well that, when we ping from client 2 to client 1, we still can't connect because FRR isn't up and running yet on the two vrouters. So let's go ahead and start them up. Okay, and let's do the same on the second vrouter. And let's just show the OSPF configuration. On the CNEP FRR instance, we can see the .19 and .20 networks being added to the same OSPF area. And on the second vrouter instance, 20 and 21 also being added to the same OSPF area. So if we show IP neighbor, sorry, OSPF neighbor, you can see that 1.1.1, which is the CNDP FRR instance IP address, is recognized as a neighbor. And the same on the CNDP FRR vrouter instance. And now the routes should be learned. So let's try and ping from client 2 to client 1. We can ping. Fantastic. And if we see the new, if we see the IP route information on CNDP FRR1, we can see the 172.21.0.0 subnet being added. Same on the CNDP networking stack. And just to show you that ICMP information isn't actually passing through CNet stack. There's no stats actually implementing for any of the input nodes here. And if we kill that and we just try and run an instance of iPerf to show UDP show UDP traffic traversing the CNDP networking stack. Okay, and let's try and connect to that via client 2. And now let's look at stats. And we can see calls to the IP4 input node and IP4 forward node actually going through CNDP. Okay, so essentially we conducted a bunch of performance tests with that vRouter example that I showed you using different deployment models and different scenarios as well in terms of networking interfaces, topologies, and so on. And what we found was for AFXDP, there's currently a dependency on the deployment scenario. For scenarios where you have north-south type traffic and AFXDP in native mode, your application can actually yield comparable performance to the PDK. For east-west traffic that originates from a vETH and is terminated by a vETH, there's a significant cost associated with AFXDP working in native mode. There is a degradation in performance. However, if you actually use AFXDP in generic mode with east-west type traffic, starting and ending at a vETH pair, it actually accomplished some pretty decent performance. It was a lot better than AFXDP in native mode or Linux stack. So there needs to be some optimization work for AFXDP in native mode for vETHs. But overall, the performance was very promising for AFXDP in the different scenarios. So let's summarize what we've discussed up to this point, and let's talk about how this affects Edge. Certainly eBPF development for infrastructure, networking, and observability is well underway. There are a lot of challenges with it, including root privileges, a steep learning curve, lack of high-level orchestration or management tool, and lack of a standard way to distribute images across your nodes. So taking all of these things into account, how can you use eBPF for Edge? I think it's still a possibility to be able to use eBPF for Edge if you leverage things like AFXDP and CNDP to allow you to do that. I think these things will meet the performance needs and the footprint needs as well for Edge use cases. But of course, AFXDP itself also has some challenges still, including the need to optimize east-west traffic performance for vETHs, especially if AFXDP is operating in native mode. And the last thing that we need to resolve for AFXDP really is its capability to take advantage of NIC offloads. There's currently 2 proposals on the BPF mailing list about, I guess 2 different solutions to allow us to take advantage of these NIC offloads. It certainly will be great to see convergence towards a solution that allows us to take advantage of these offloads in the longer term. So certainly the eBPF revolution is happening. Please feel free to come join us and take part. The more, the merrier. I've just included some useful links at the end of the talk here, including one to BPFD, one to CNDP, and a really interesting paper on CNDP and how they were able to abstract out the privileged parts of eBPF to be able to launch unprivileged CNDP pods. And that's really it. Thank you very much, folks, for your time. I really appreciate it. And sorry I couldn't be there in person. Thank you.